column spacing are of the order of magnitude of sphere upon structure, which is a very tiny little number, divided by the mass, some measure of the range of confinement squared. So it's only for very, very small masses and very fine and tightly confined objects, if you like. It's only in those cases that this ratio gets anywhere close to numbers, energies that we're accustomed to. That's why we don't see it in except in small situations.
Yeah.
So, I'll post all this, I'm just going to run through it very quickly. But the typical orders of magnitude in various modes of molecules and gases. Recall that the energies that are available. So we've got a molecule, and it can have energy because it's moving around in the box. That's translation energy. It can have energy because it's tumbling. It's not a single atom or atomic molecule. It can have rotational energy. It can have energy because it's shaking internally, vibrating. It's interacting with other molecules by collisions, banging around. And so this energy is always shuffling in and out of these modes. And it's an average energy that we're talking about for the gas and equilibrium. And the mechanism it has for it being transferred from one level in a given mode to another level, or from one level in a given mode to some other mode, mechanism of these shuffling around are through collisions, through impacts. That's how the energy can be distributed. So it is the collisional energy that determines how effectively the energy will be distributed throughout this network of possible repositories. The energy of collisions on average is related to KT. We know that's the order of magnitude of the average collisional energy. So that's what I like to think of as the little Tasmanian devil that's running around here kicking all these things and exciting the energy, getting energy into these various modes. And if it's got, it's a case KT for at room temperature is about 0.26 electron volts. That's a certain amount of energy. And that's about how far it can kick something uphill. You know, of course, there's Maxwell's distribution, so some of them have a hell of a lot more than that. They can go way up, but we know that falls off real fast. You've seen that. That falls off real fast. So if the quantum spacings are very much smaller than KT, then for some mode, then that mode's going to be essentially fully excited classically, because the stirrer is energetic enough to scatter things around and fill up statistically as well as possible. But if the quantum spacings are big compared to KT, so in the ground state is down at this level, and the next one is way up there, and KT is like this, it's not going to knock many of them up there. And that mode's going to be pretty empty. And of course, if the quantum spacings are of the same order as KT, the same general magnitude, then what happens? Then that mode will be partially populated. The collisions are indicated enough to knock some molecules into excited states of various kinds, but not classically populated. It won't be enough to get the implication out. Does that make sense? That's sort of the picture I have. So consider some typical values for small molecules. I don't want to look at big polymer molecules or DNA or things like that, but we're talking about gases originally. There's not many gases. So for ordinary gases, order of mass is 10 minus 26 kilograms or thereabouts. For translational modes, we're in a box of finite size, and the spacing between typical translational levels are tiny. They're essentially zero compared to KT. And consequently, we cannot see quantum states in translation. Looks like energy just can be continuously, very continuously from one place to another without any gaps. We're not aware of it. So we don't worry about it there. And consequently, translation is always fully excited. 1/2 kP per translational mode at equilibrium. 1/2 RT per mole translation energy in a given direction. Rotational modes now, the box's confinement is smaller, so I take it as sort of magnitude of the circumference of an atom or a molecule. It's an angstrom across, and it's 3 angstrom. It's 2 angstrom across, and it's 6 angstrom. So a few angstroms. Well, then we get the spacings between these quantum levels are down magnitude of, say, 10 minus 4 electron volts, and that's still smaller than KT at room temperature, which is 0.26. And that means that KT can excite them pretty well. And rotations are nearly always fully excited. Especially cold, lower the temperature enough so that KT gets smaller and smaller and smaller. But as you get it low enough to calm down the rotations, these gases always end up liquefy and solidify, so that it's not very good. You can generally assume rotations fully excited classically. So how about vibration modes? Well, here the box, the mass is about the same, but the box is very much tighter because now we're talking about something just making them tiny excursions of vibrations, not topping around like that. This kind of stuff. Shake. And the order of magnitude of the vibrational quantum levels in typical molecules, there's the order of in minus 1, 10 electron, and that's getting to be in the vicinity of KT at room temperature. And so consequently, at 300 K, collisions can excite some population of excited state, vibration excited states. But how much that is depends on exactly what the spacing is. It gets much smaller than Block 1, then you get a lot of excitation, gets much bigger, you get, but we expect to see something in some molecules. So where do you look, how do you measure these spacings? You measure them in the spectra of molecules. When you study that part of physical chemistry which deals with molecular spectra, you'll learn how to do this. And we find that we can actually measure them in real molecules and know what these spacings are. So for translational states, we know they're going to be essentially zero. We're not going to see the wavelength. If you find that is beyond anything that we can hope to measure, the tools would have. So we don't worry about quantum effects in translation. For pure rotation, just the rotational spectrum, those are sort of in the microwave region, like that, or some wavelengths. And they're measurable. You can write them down. For vibrations, they're in generally the infrared region, and sometimes you can see pure vibration spectra, and more often you see a combination of rotation and vibration spectra that are defined in the infrared region. They can be measured. we know what those gaps are. Let's look at an example. Nitrogen gas at 300 Kelvin. We've seen some of this before. Let's write down some measured properties of it. Heat capacity constant volumes, 2.503 R. We had this yesterday, I think. That's equal to the full expedition, 3/2 R for translation, the full 2/2 R for rotation, and what's left over is this little whisk. That must be the vibration. So we can say that the nitrogen gas at 300 Kelvin, that if it were fully excited, this would be R. But it's O3 excited, it means it's 0.3% excitation. That's 0.3% of the classical value that I have for the spaces and the box. Pretty easy. Well, that's not very much. The ratio of heat capacities is 7/5, approximately. It's 1.4012, about 7/5, because there's not much vibration. And the spacings are 0.29 electron volts, and those are measured in the spectrum of nitrogen. So that's a experimental measure. So if your Tasmanian devil's running around with 0.026 electron volts of energy, how many nitrogen molecules is going to excite up to this first excited state, which is 0.29 electron volts up? Very, very, very few. That's what this suggests. There are some excitations, but really not many. Well, let's look at some other diatomics. At 300 Kelvin. And we'll look at the heat capacity constant pressure, the molar heat capacity constant pressure, the molar heat capacity constant. That's heat capacity constant pressure. This is the vibrational contribution, which we find just like we did for nitrogen. Take deuterium, small molecule. You can't find any vibrational excitation. Why is that? It's a very, very small molecule and a very strong bond and very light things out on the end that make that foot really stiff. They're heavy and massive, then they can move fairly easily and spring squishy, but they're light. That is really stiff. That's not even surprising. Fluorine is a diatomic molecule that has somewhat more mass than atoms and not quite as strong a bond. So we get about 26% of the heat partition value of vibrational excitation. Chlorate, a little heavier molecule, and just easier to shape. And we get about 58%. Now I put oxygen in here, and I realized I couldn't do that, and I'll tell you why. So I'll scratch that out. Nitrogen, we just talked about that, 0.3%. Here's one, K2. Where you say, well, potassium doesn't form a molecule of K2. Well, sure it does, but only in the gaseous state. You can't have a lump of it or a molecule because it's a limited gas. And mostly in the gaseous state, potassium vapors just atomic potassium. You can't have these molecules. It's a whooshy little molecule, about 99.8% vibrationally excited. Well, why is that? Because you've got pretty good sized atoms out there called a very loosey spring. Now, I've got two springs here. So we're talking about vibrating all this. Kind of pretty good. It's nice and stiff. Potassium spring. That's much easier to excite. So there's a lot of is highly excited vibrationally because its atoms are little, or massive, not much. But principally because that bond is very weak, very squishy. The spring is it's easy to excite. Now, how about oxygen up there? Well, I wrote that down. I saw, well, oxygen is not much different than nitrogen. It's got a pretty stiff bond, it's a small molecule. And shouldn't be that much vibrational excitation, not 10 times what there is in nitrogen. Of course, there's not. It happens that oxygen molecules have other kinds of energy that we haven't talked about yet that can contribute to their heat capacity. Most of them don't do this at ordinary temperatures, but oxygen has a low-lying or some low-lying electronic loads, and that even at room temperature, some oxygen molecules are electronically excited, and there's heat capacity associated with that. There's another box, another repository for the energy the molecules share. So oxygen is an outlier in that respect. You'll study that when you study that part of physical chemistry. So note that the vibrational excitation in gases varies with bond stiffness, as I said, and the atomic masses, but especially with the temperature, because that determines how strong you're agitating these molecules, how vigorously they're being stirred up, and how easy it is to excite out of the ground state. So I generated a chart here, a graph, a variation of the reduced constant volume heat capacity with temperature. So let's look at that. Here it is. So the constant volume heat capacity of molar value divided by R. If the molecules are fully excited for the equal partition theory, this will be 7 halves. 3 halves translation, 2 halves rotation, and 2 halves vibration. 7 halves. If there were no if there's no vibration at all, just translation and rotation, then it would be 5 halves. The vibrational contribution fully excited is 2 halves of R. If there's none of it, then take that away. All right, so here we are, 300 Kelvin, right down here on this 5 halves line, about 0.3% above it. And you raise the temperature up 1,000, 2,000, 3,000, 4,000. It does. And what's it pretty clearly doing? It's pretty clearly heading for this asymptote, which is 7 halves. Now, if you did this with oxygen, it would come up here and cross that and keep going a little bit because of that electronic contribution. That's why you would do that. Well, that's pretty exciting. So note how the vibrational excitation increases as KT increases. That's because the higher the temperature, the more vigorously your magnets into one another, and the more likely you are to get excitation in these vibrational modes. So here's a sketch, crude sketch. It shows the parabolic potential well at the bottom of the nitrogen molecule. And the spacings down there are 0.29 electron volts wide. And at 300 Kelvin, we got this little wussy thing. How many molecules can it kick up to there or there or there? Not too many, not too often. So not going to be many there. Here, 4,000 Kelvin, we got out that far. I didn't put it out there. We got out far. The spacings 0.35 electron volts, which is a good deal bigger do some real, create some real action. Indeed it does. See? Wow. Well, that was a little diversion into some, that was having to do with molecular properties and their pharmacological behavior. I got one more example here. I guess I better do this. Carbon dioxide. Carbon dioxide is a linear molecule. And we normally represent it like this with double bonds. It has 3 atoms, such therefore 9 degrees of freedom, 3 translational, 2 rotation because it's linear, and 9 minus 5 is 4 vibrations. At 40 degrees centigrade and 100 bar, this is its heat capacity, measured heat capacity. This is its Joule-Thomson coefficient, measured Joule-Thomson coefficient. This is its expansion coefficient, thermal expansion coefficient, measured coefficient. This is the compressibility, the isotopic compressibility, measured property. And then I say here, let's calculate the difference in heat capacities. And you remember we have this equation. So I'll count here. So I've done that, and we get, these are just numbers, put them in there, boom. And for that, I get the volume heat capacity, sorry. All right, so we got that. Now, the cost of volume heat capacity, if you're fully excited for the heat partition, would be the translational contribution, the rotational, the vibrational would be 3 halves R, 3 halves R, and 4 R. Be 6.5 R. But it is 5.2 R instead. So we can calculate percent vibration, excitation of CO2 molecules, just like we did for nitrogen and those other diatomics. Under these conditions, the classical minus the experimental is 1.3 R. That, if it were fully excited, would be 0, and the vibrational contribution to heat capacity would be 4 R. So we get the percentage difference by taking the difference from that 4 is 2.7. Here it is. 2.7 R divided by 4 R times 167.5%. So even at room temperature, there's a good bit of excitation in a molecule like CO2. It's big enough that it's easier to excite. However, these 4 vibrations won't be excited equally, I don't think. So what are those 4 modes? Well, I've tried to draw them here, not very well. First one is a symmetric stretch. So this molecule moving out, that should be a straight line there, straight line there. And this molecule moving out, it's doing this. And the carbon is just sitting there. Symmetric stretch. Then the anti-symmetric stretch, this oxygen goes toward the carbon, which pulls away from that one as it pulls away from this. So you've got, I can do this, see. Which of those you think would be the represent the greatest confinement, if you like, or have a higher spacings? The symmetric stretch is easier than one doing like this going in while that one goes out. I think the symmetric stretch should have smaller quantum spaces than the anti-symmetric stretch.
So for the symmetric stretch, the oxygens are pulling away from the carbon, but is the carbon pulling in?
The carbon's sitting there, it's symmetrical. See, the center of mass of the molecule's fixed. We're talking about vibration. So the oxygens move, and the carbon doesn't move. But in the asymmetric stretch, one oxygen moves toward the carbon moves toward it. As the carbon moves away from this one, keep the center of mass fixed. This one has to move out. Now you have to think of these molecules from the vibrating. The center of mass is fixed, and then the atoms are moving around. So if there's motion somewhere, there has to be some other motion to keep the center of mass fixed. And for this, all it can be is those oxygens moving. Now, then there are two bending modes, and they're identical. So here's our oxygen atoms out here, carbon in the middle. There's a bending mode like that, and a bending mode like that. These are, they have the same spacing. Now, which of these you think has the smallest spacings? We think that this is one of the biggest spacings. Represents the most restricted motion. This one next, these should be smaller. And you can see that. Look how much easier it is to bend that thing than it is to stretch it.
Would you be able to move the paper up a little bit?
So then I just say, which of the vibration modes in CO2 do you think are the least populated, have the largest quantum spacings, which modes are the most populated? And we just answered that. The least populated one is going to be the antisymmetric stretch. Then slightly more above that would be the symmetric stretch. And then a good way above that is these bending modes. And of this 67% or whatever here, most of that's in those bending modes. There was. Okay. Now that finishes my little excursion off into that branch. But I do want to remind you, day one, I think it was, we talked about physical science, and I said there were 3 questions that are central to the pursuit of science and the study of science, and activities associated with seeking answers to them. And those were the ones I wrote down. What's the behavior matter, what proves shown behavior matter, structure matter that causes the observed behavior. And then on the next page, you may not remember, but on the next page, I said this scheme is flawed. I think it was good enough for us to get started. As it was. Now we've seen some at a peak at this point. We've had a peak because what we've had to do to get where we are. We've had to say that energy is quantized, that knocking a frog off the moon pad with a rock is just expected to say that knocking them off with a wave, but it can't be. We said a lot of stuff that just doesn't make sense. And we said that, the reasons I told you yesterday about the arrogance of our species. And you won't, this is probably the only time you'll ever see this. I'm sure you won't find it in your books. When I'm teaching where I can go into this topic, then come back and modify this. The reason we're doing it is a lot more compelling than what I've told you thus far. Here, it's just a scratch the surface. But we can't, see, human beings, we can't ask this question. We can't say, what is the behavior of matter? Because we can't know. Not on the atomic molecular level, because we have to disturb everything we look at. We can't know. So that's an arrogant question that we are not proud to ask because of our limitations on how we acquire information. I won't find any scientists who will agree that that's a reasonable statement. This practical statement. So we can ask that question. You could say, what is the apparent behavior? You could say, how does matter appear today to us, the way we're able, with our senses and our extensions of our senses, to perceive it. What's the apparent behavior? You say, well, that's not much difference. That's a huge difference. That's a huge difference. What problems govern the behavior like? What rules govern the behavior like? Who the hell knows? What rules govern the apparent behavior? Not what the laws of nature, what the apparent laws of nature. Try to be a little humble. Study science this way. Yeah, be a little humble. You study science and not just and then this section, what is there about the structure of matter that causes the observed behavior? I'd say, what might there be? What might there be about the structure of matter that causes the perceived behavior? Now those questions, my friends, are the questions of science. Should be. Could be. Think about it. All right. Now, get back to the real exciting world of mathematics. We're going to talk about work of expansion of ideal gases. We've already talked about this some. You need to expand. Suppose I have an ideal gas, pressure, volume, plot. I'm going to show the expansion. And I start here at P1 and P1, and I come down here somewhere to P2 and P2. And if I do this at constant temperature, then I would follow, do it to get the maximum work area under this curve. I would follow Boyle's law, PV. So this would cover that if I did a high circle. And we said we had the little imaginary apparatus, frictionless, weightless piston plate. And we said if we let that expand reversibly, the work that is being done to lift the mass or push it back on the applied force is coming at the expense of the molecules in the gas. And as they're losing energy from doing this work, the temperature should be going down because their average energy goes down. To keep it up, you have to flow heat in equal to the rate at which they're doing work to keep the temperature constant. Okay? So I ask you, what would happen if we started right here and carried out that same experiment? One of the little decimal grains of sand, we split off and push the weight up. Now we do that same experiment, except this apparatus is going to be completely adiabatic, no heat flow can go through the ball. And we're expanding up the same volume. What would be the difference?
Would the temperature not be constant?
No, it would not be constant.
Yeah.
The gas, it's not isothermal now.
Right.
The gas is doing work to push that mass up. Its temperature's going down. What would it look like if we did those two experiments side by side? From the isothermal one, we come up this far, we did have a mound of sand on it down here. Now we've got a truncated mound up here. Adiabatic would bring it up the same height. We had the same mound on it when we started.
You have less.
Yeah. We would have have listed less plants, right? We could have done less work. So you don't have to be a rocket scientist to figure out that if we come down adiabatically, we're going to come on some line that's below that Poisson line. And all points in this field under that line are at lower temperatures. Okay? All points in this field above that line are higher temperatures. So the temperature is changing as you come down. I just want to understand that this is isothermal. This is adiabatic. And I'm going to just reverse it later, but if it does not raise the sand, and I want to know P equal to what function of V. Here, this is P is proportional to 1 over V, and here we need to know what that is. That's what we'll find out here first. So we know why it falls off from a mechanical point of view. We come down and say, so here's V1, here's V2, here's P1, then this P2 is higher than this P3, right? So, we want to know what is the adiabatic at, and work done on the surroundings. The expansion proceeds. That's what we got to figure out. Well, let's start with a statement of the change in state, where I'm going to assume we have n moles of an ideal gas at initial pressure P1, initial volume V1, initial temperature Q1, and our final state is n moles of ideal gas at the final pressure of P2, a final volume of P2, a final temperature T2, and we're going to have Q is equal to 0 because it's adiabatic. I can't say Q is constant out there because Q is not anything other than energy in motion. So I'm saying there is no energy moving into a temperature difference. Right. So for this process, we'll have P applied, this is the pressure gas, and that's at R E over V. EQ is everywhere 0. And dW is equal to minus P applied dP, and that's minus n RT over V dP. And I'll call that equation 1, lack of a better number. But recall that in general, heat capacity at constant volume is derivative of the energy with respect to temperature at constant volume. But, special case, ideal gas, we have energy as a function only of temperature. Therefore, still CV. Therefore, EU along this path will always be equal to CV dt n times CV whole times dt. We'll call that equation 2. So clearly, equation 1 is equal to equation 2. If we can equate the right-hand sides of them, and we get minus nRT over V times dV is equal to NCV dt. And then we play around with this to get rid of the n's, doesn't matter about them right now. All right, minus R over CV times dV over V is equal to dE over T. And I can write minus R over CV times the root of the logarithm of V is equal to the root of the logarithm of T. Or I can integrate this to get minus R over CV times the logarithm of V is equal to the logarithm of T plus some integration constant. And I can put these on the same side over here and write R over CV times the logarithm of V plus the logarithm of T is equal to some constant. Make that one. And I can write R, we'll take this up here, all right. The logarithm of V is R over CV plus the logarithm of T is equal to constant. And then I know that what I can do with logarithms, I get the logarithm of T times V to the R over CV is equal to constant. Or if the logarithm of something's a constant, then something's a constant. So I write TV to the R over CV is equal to constant. And why not recall CP minus CV for ideal gas only? If I know that now, the condition for sitting is an ideal gas is equal to R. So I get, finally, I have the already, last week I wrote that. I have T, V to the R over CV, goodness, T, V to the CP minus CV over CV. And that's equal, it's a constant. And that's equal to T, V to the 1 minus, I'll walk to the gamma minus 1 power. Gamma is equal to CP over CV. Well, if you like, that matter. So we have an equation here. Pretty important. Gamma minus probably that number would be my actual 3. But that doesn't tell me about that path on the TV diagram. So I want to get rid of the temperature in favor of pressure. What's the temperature? big time equations that we need to, even use to have access to as needed basis. And I'll be referring to those equations, again, a little later on in another context. So, one of the values of gamma. Gamma is Cp over Cv can the constant volume heat capacity of gas and be more than the constant pressure heat capacity of gas? No, it cannot. So, one, zero less than gamma goes on up. Highest gamma can be is anyhow, the important thing is that gamma is greater than zero for how many gases? Okay, zero for the gas. So consequently, back to our question, start here, come down, isothermally, E, V is equal to constant. Then pressure falls off as a reciprocal of the volume. Come down on an adiabat, first adiabat, we have PV gamma is equal to constant. But the pressure falls off as 1 over V gamma. And gamma is bigger than 1, so it falls off faster. Proves what our gut feeling was at the outset. What makes sense. It should fall off faster than the isothermal reasons we mentioned. So now we're going to work at this thing. Calculations. Action. That's an ideal gas. And no vibrational excitation. We can put it in, but we're just making this simple. No vibrational excitation, so that constantly the molar energy is 3 hash for translation, 2 hash for rotation is 5 as RT. The heat capacity at constant volume is 5 as R. The molar enthalpy is the other side. Oh. It's energy plus PV, that's RT per mole. So it is 7 halves RT. Heat capacity constant B1, B1 to B2. Can't say to B2 because those are different from going on the ISO back and going on the ADI back. We're going to expand from the same initial state to the same final state by 2 paths. Path 1 is reversible isothermal. Path 2 is reversible adiabatic. Now let's give this some specific numbers we play with. We have N moles of nitrogen, ideal gas, and just make these numbers up, 6 atmospheres and 2 liters and 300 Kelvin. And we're going to N moles of nitrogen, ideal gas, at a lower pressure, say 3 atmospheres, and a higher volume, let's say 4 liters. So we go by the isothermal bath, final temperature will not change. We'll write that out. Very tedious. Oh, it's our system. And that's that whatever I said is 6 atmospheres. And 2 liters. Two, 3 atmospheres, 4 liters, still 300 Kelvin. And we have that du is Q plus W Q minus E applied to V is equal to 0. Isothermal process ideal gas, no change in energy. So that EQ1 is equal to minus EW1, and this is expansion process, and minus EW1 is plus E applied EV. P applied is N R T over V EV. And we integrate that and find Q1 is equal to minus W1. We did this the other day, so we write that as N R T log of P2 over V1. So we got all that. Now let's do the adiabatic gas. Put numbers. Yeah, so this is what NRT. All right. Now, if I gave this problem to this class, as far as those other classes I've known, first thing you do is sit down and find out how many moles I didn't say. Okay? And write down the number of moles you just gave you a fresh result. You can do that, that's fine, but I wouldn't do that. Personally, that's just extra work. Every time I do a calculation, there's another chance to make a mistake. If your calculation do, the less chance you're going to make a mistake. So I would just say that NRT is equal to V1, V1. Got it, guys? That's where we started. It's also P2, V2, V1. And then we have the write this out? I have done it, so. You could just write it out and say that's the energy of meter atmosphere, which is even energy. I would do that. If I want the energy in joules, then the way I normally do it is this. I've got meter atmosphere here. I don't want meter atmosphere, I want joules. I know the gas off constant's 8.314 or 4. Remember that. Joules per mole per Kelvin. And I know it's also 0.08245 meter atmosphere. So there's a conversion factor. I have to look on that. Cancel meter atmospheres. I get an answer in joules. It's 842.9 joules. Ooh. And also write down what is delta H. We've already said delta U is 0. Delta H is equal to delta U is equal to 0 if there's a constant. I want to compare those numbers to what we get for this cat. And for this, we have P, V, and gamma is equal to a constant. So that we can say P2, we don't know what that pressure is. It's V1 times V1 over V2 to gamma power. So that is equal to 6 atmospheres. That was V1. V1 was 2 liters, V2 was 4 liters. So the gamma power is 1.4. Solve that's 2.27 atmospheres. The lower than that, 3 atmospheres we had for the outside. Now we know that PV to the gamma minus 1 is equal to constant. Therefore, T is equal to T1, V1 over V. T2 is T1, V1 over V2 to the gamma minus 1. So that's 300 Kelvin, and V1 is 2, and V2 is 2, so it's still 2 over 4. And gamma minus 1 is 0.4 power, and this comes out to be 227.4 Kelvin, which is also equal to minus 45.8 degrees Celsius. We're going to cool the P1 out of that nitrogen just to double its volume adiabatic. It's compressed as high as it was to start with. All right. Yes, add delta T is equal to T2 minus T1, and that's equal to minus 72.6.
Can you scoot the paper out? We didn't see what you just wrote. Oh, thank you.
Try and write this so you can read it, so you read when I post it. So now we're still on path 2. Then we're going to look at Q2 is 0, it's adiabatic. Minus W2 is equal to the integral of P applied dV. The applied pressure, well, we have to figure out what that is. P applied is equal to pressure to gas, which is reversible, is equal to what? Well, we know that T1, V1, the gamma power is equal to T, V, the gamma power, anywhere along that curve. So our pressure is V1 V1 to camera power, and that's the integral to V1 to V2 of dV over d camera power. Wow. So then what would you do? You're asked to calculate this. All we need is all that integral. Put in the limits of the answer. I submit that's just more work than I feel inclined to do right now. So let's look at recall that DU2 is DQ2 plus DW2, and this one is a 0. So that work up there is also equal to NCV. So that minus dW2 is equal to minus NCV dt, and minus W2 is just equal to NCV delta T. We just calculate delta T. Oh, how much easier is this? You say you still got to calculate the number of moles. No, say no, I don't care. If I don't ask you how many moles there are, then no reason necessarily to now. I didn't ask about it. So how do we look at this? Well, what's N? That's equal to P1 V1 over RT1. That's the ideal gas law. And what's the CV? All right, no vibrations. So there's 3 halves R for translation, 2 halves R for rotation. So that's 5 halves R. And what's delta P? Well, we calculated that a minute ago. Got that. We don't need to leave R's. We've got to calculate this. So we got, right? We got minus W2 is equal to P1 V1 over P1 times just 5 halves times delta T. Let's put it. Yep. Yeah, I guess we got that minus sign. Never need that minus sign. All right, so let's put the numbers in. V1, V1, we know that's 12 meter atmospheres. P1 is 300 Kelvin. I'm not quite sure what 5 halves, look that up. And delta T was minus 72.6 Kelvin. Hold on. We had 7.2 centimeter atmospheres. Going in joules, small by 8.3144 joules over 0.8205 liter atmospheres, and you get the answer to 735.7 joules. Compared to what was 842.9 joules for half one. What we said, you want to do delta U at two is equal to W2 is equal to minus 735.
Can you move it up?
Yeah. Okay, let me tell you what, everything's done here. Everything's done. We know delta U for this process, delta H at 2 is just equal to NCP delta T, and that's just equal to NCV delta T, which we just calculated, times gamma. So that's easy to calculate. We should get minus 1,030 joules. All right. So, and I'll put this on. I'll go ahead and finish this. If you're
Why would you have
Notice
to
that
get
little
to the
table.
camera?
Be preparing Q, minus having the work done in the
Yeah, that's what I
surroundings.
was just gonna ask.
Delta U, delta H, at 1, at 2.